All right, so this is a cell, and whenever we measure the voltage across a cell, what do we call it? Fairuz, Nawal Mugdo?
EMF.
EMF, yeah. Why are you so scared, man? Be more confident. So whenever we measure the voltage across a battery, we call it EMF. Yes, we used the same color yesterday, actually. So one of the common questions they ask is, say this has an EMF of 1.5 volts. So if I put, say, multiple of these together, I put 4 here together, this is when we call it a battery, right? We can draw it like this, or we can also draw it like this. Fundamentally, it means the same thing, multiple cells together. Here you can actually count the cells. Here you can't count the cells, but if they do give a diagram like this, usually they will add in a bit of information in the writing. So what's going to be the EMF of this setup? Bolte parba? Magdo?
Just add it up. 1, 2, 3, 4.
Yeah,
So
and that's
6
going to be 6 volts, right? That's right. So the EMF of this setup is going to be 6 volts, correct? And the same thing here, the EMF would be 6 volts here.
But it to bole dibe, right?
হ্যাঁ কোথাও অন্য কোথাও লেখার মধ্যে ওরা বলে দিবে যে this has an EMF of 6 volts. So a question we come across a lot, and even a question that even we came across today, is what's the difference between me having, say, a cell like this, and say I take 3 cells, put them like this, and 3 cells in parallel like this. So Mugdo, can you tell me what will be the differences between these?
Are they the same identical cells?
Yeah, they're the same cells, all having an EMF of 1.5 volts. Now, how would you work with this? What would it mean, or what would it do?
Well, the second one is obviously the sum of each individual.
Yes, so if you have 3, then the EMF is going to be 4.5 volts, right? What about this one? What do you know about this? Guys online, what do you guys think it's going to be? Oh, don't worry. So yes, the correct answer. Good job, Zabir.
Because it's connected directly to one.
Yes, now basically what's going to happen is, yes, it's going to measure the EMF across each one of them. So each one has an EMF of 1.5. So the EMF across this whole setup, if I take a voltmeter and measure it, I have to use the blue. Let's just use blue here. So the EMF is going to be 1.5 volts. So the thing is that a lot of people ask that if this is the setup, then what's the difference between having 1 cell and 3 cells like this? Can anyone tell me what's going to be the advantage or the difference of using this setup compared to this setup? Why would we use it? Any questions? Any ideas?
Is it like actinostrable or something like that?
Well, that's one of the things that we could do. What happens here is basically, if this is the positive terminal, if this is the negative terminal, if we have a current of, say, 1 ampere flowing through the root, what happens is this current splits into 3, right? Taina? Fairuz?
Yeah.
So, gotcha there. So basically what's going to happen is it's going to be 1 by 3 here, 1 by 3 here, and 1 by 3 here. So the current splits into 3. Basically, it draws 1/3 the current it would from each one,
So
compared
is it like, protecting the...
It doesn't protect it exactly. What happens is, as Nawal has already said, that's pretty cool. Lasts longer. If one breaks down, another still works. That's one of the answers, yes. That's not wrong. But yes, the best answer is that what happens is that, yes, it's going to last longer because each one draws less current. So it's going to operate for a longer time period, and it's going to be better. So that's basically what happens here. This is the advantage of using a parallel setup. Please remember, the EMF does not increase. The EMF stays the same. If you have 4.5 here, that's because they're in series, but when they're in parallel, the EMF remains the same. What does split is the current for each one, making the whole setup last for longer. All right. Good try, Nahrin, but not there yet. This is one of my psychology students, actually. She's actually poking around with physics, which I'm very happy about. The fact that,
Hey, I'm going to be a physics and psychology student in a few months.
Really? Wow. That's going to be...
man.
That's really bad for me. That's horrible news for me, but...
Hey, you
let's
can
see.
get through this, man. You can get through this.
Yeah, I might just stop teaching psychology. That's an option. So this is one of the things that I wanted you guys to watch. Another thing that I need you guys to know is that, all right, what's going to happen if I do this, all right? So we have 4 cells in series. So the EMF is going to be obviously 6 volts. However, say I give an IGCSE student to set up a circuit, and something like this happens.
একটা করে ফেল
1, 2, yes, let's use a different color. We flip one of them accidentally because I GCSE student. And then we have this. Right? So what's going to be the EMF across this? Come on, guys.
It's going to be 0.
Huh? Okay, one option is 0 volts. Anyone else? Any other answers? So this is going to be 1.5. We got a few answers. We've got 0, we've got 6, we've got 3, we've got 4.5. One way, you are not on your game tonight. 1.5, 1.5. What's going to happen here? This is going to be minus 1.5, right? And this is going to be another 1.5. So what happens is 1.5, 1.5, minus 1.5, and 1.5. That's going to be 3. So the correct answer is actually 3 volts. So let's move on. Now let's start making a few more complex circuits. Let's try something like we take an EMF of 9 volts, right? And we connect it to a circuit which is like this. We put a, all right. Ooh, here we go. So say this is 5 ohms. Say this is, I don't know, give me a value.
2.5.
Oh my God.
Okay, 3.
Okay, 3 ohms. And this is?
2.
2, nah, that's too
Oh,
easy.
sorry, I don't know, 10.
Okay, 10, 10, nah, not 10.
7.
7, yes, 7 ohms. All right, so say we have a setup like this and we need to figure out the voltages across each one. So yeah, we have a very simple circuit set up here. Let's figure out the different values that we're supposed to experience at different points of this circuit. So, say for example, if this is the circuit setup, we want to find out, again, these are the questions what I always tell you, focus from outside towards in. See the big picture first. Once you see the big picture, then focus into each one of the components. So if I see a big picture here, what I mean is now step number 1 would be find total resistance. Right? So, Mugdo, could you tell me the total resistance of the circuit?
1 by 5 plus 1 by 10.
Yeah, that's right.
the
So,
inverse of
did
that.
you bring your calculator? That's an imaginary calculator. You can't use that. But yes, guys, please always bring a calculator. You're going to need a calculator for these sort of questions. And yes, if I ever invite you, do not forget your calculator. So 10 ohms. This is the resistance across this, right? And there's supposed to be a calculator somewhere around here. So here we're going to get 10 ohms across this setup, and we're going to get 5 ohms across this setup, right? So the total resistance of this setup is going to be 1 by 10 plus 1 by 5 to the power minus 1. Right, so we have a few answers already. Qazi Farhan Labib has already said 3 ohms. Did you find a calculator? Oh, it's the white one, right? Don't you like it?
Yeah, it's a white one.
Yeah, I like it. Nothing racist there.
I got like 3.33333333333333.
Okay, according to Mugdo's calculation, he got 3.33 ohms.
3333.
Okay, so if that's the case, then what do we have? We have basically 3.33 ohms as the result. So once we have the total resistance, the second step is finding the total current. Right? And what will the total current be then? Total current is going to be I is equal to V by R, right? So is V is 9 divided by 3.33. That gives us how much?
2.7.
2.70. 2.70, all right, amperes. So that's the current through this route. Let me draw the amount of the path that is going to carry a current of 2.70 ohms. How much is it going to be? It's going to start from here up to here. And on this side, it's going to be from here up to here. The green part will be carrying 2.7. Yeah, 2.7 ohms. This is assuming that Mugdo's calculations are correct, by the way. Right, moving on. Then what happens is the current splits here, and you get one current through this route, and you're going to get another current through this route. Right? Now, can you tell me why these currents are not going to be equal?
Because actor resistance, actor resistance beshi.
Yes,
So
basically there's different resistances
current
for
tries
each
to
route.
take the path of
Well,
Not
it
in this
does.
case.
Well, it does. Basically, you'll have more current through here, but less current through here. You're going to have current through both routes, right?
in this case.
Yes. So what's the voltage across the 5 ohm resistor? Look at the question. Look at this. What's the voltage across the 5 ohm resistor? Keep
Because
your
2.7.
keep your mind in the zone. No, it's 9 volts.
9 volts.
Right. So it's going to be 9 volts, and we have 5 ohms across it. It's 5 ohms resistance in it. So what is it going to be? I is equal to V by R. So V is going to be 9 9 divided by 5,
1.8.
which is going to be 1.8 amperes. So that's the current for this route. And what about the other route where we have 3 and 7? What's the total resistance of this route? 10 ohms.
10 ohms, sorry.
So 10 ohms and 9 volts. So it's going to be 9 divided by 10. You don't have to do maths for that. It's going to be 0.9 amperes. Right? So look at this. It matches up really nicely. We get 1.8 amperes through this. We get 0.9 amperes through this. And it adds up to a total of 1.8 plus 0.9 is how much? Mukto?
1.8 plus 0.9. Geez.
I have to make a better way of, like, switching different colors. Plus.
Get like a
and then you try pushing all of them together and then it gets stuck, right? Which is equal to
2.7.
yes, 2.7 amperes. That's right.
Hey, that's the total.
Yep, that's the total, man. Mind blown, Naki.
Man, yeah.
Yeah. There we go.
That's amazing.
Amazing. So now, one last step, then we're done. What's going to happen to the voltages across the 3 ohm and the 7 ohm resistor? Can you do those calculations?
What are the 0.9?
Yes, we have a current of 0.9 passing through it.
So
let's use another color for these.
Times
So V is equal to IR. I is going to be 0.9. R is going to be 3. So 0.9 into 3 is
2.7.
2.7 volts. That's the PD across this resistor. And there's two ways of finding the resistance in this resistor. Can you tell me the two ways? One way is obviously using the same route. Basically, we do V is equal to IR. And I going to be 0.9, R going to be 7, right? 6. And what's the other way of finding the value of the voltage across this? Come on.
I know the total voltage, right?
Yes, you do.
I think I can find it out from there, right?
How would you do that? V total is equal to V1 plus V2, right? So it's going to be basically, you subtract one from the other, right? So, if you subtract one from the other, how much is it going to be?
9 minus whatever I got for that one.
Yes. So, let's do both of them. So, what's 0.9 into 7?
Ratio.
Yeah, we'll do that. That's going to be the third surprise method.
6.3.
Yes, so it's going to be 6.3 volts. And if 6.3.
No calculator, yay.
Oh, so smart. No scope. 360 no scope. So what's going to be the other method? Basically, 9 minus 2.7. 9 minus 2.7 is how much? 6.3 volts. So we get the same value. Now, let's talk about this ratio method that everyone's screaming about. So one thing we know is the currents of both resistors are the same. So if the currents of both resistors are the same, we can go back to our fundamental equation, which was V is equal to IR, right? So let's draw this again here. So let's say this is 3 and this is 7. So we have 0.9 through this, which is also 0.9 here. It's also 0.9 here. Series, the current remains the same. So as V is equal to IR, and the current is the same, so we can say that basically the ratio of the voltages is equal to the ratio of the resistance. So if it's 3:7, then also the voltages will be 3:7. So one way of showing that would be basically 3 by 10, right? Total resistance of this is basically 30% of it, and this has 70% of the resistance of this, so it's 7 by 10. Basically, how did I do that? 3 divided by the total, 7 divided by the total. And I can just multiply this, as it's a ratio, I would multiply this with the EMF across this route, which is how much? 9 volts. I don't even need the current to do this, right? So you don't even, if they ever ask you a question where they want you to directly find the voltage and they haven't given you the current, then that's an easy way of doing it. So this into 9 volts. And what will this give you, Mukto?
Let's see. 9 times, what's the sorry?
9 times 3 is 27 divided by 10, 2.7.
Okay, chill, man. I did it mentally too.
Yeah, I just did it faster. Flex. All right. Well, it flex na kule kiya flex ko. So 7 by 10 into 9, right? This is going to be the same for this 7. So it's going to be basically 63 divided by 10, which is 6.3 volts.
Did it faster.
I just gave you a chance, boy. All right, guys. That's the basics of this. So we've pretty much got this done. Quick maths.
Inception.